This video is part of the series Forensic Physics: How Science Solves Crimes in Court. In this series, we explore how the laws of physics are applied to crime scene evidence and how scientific reasoning supports legal decision-making. Each episode focuses on one physical principle and its forensic application. This educational initiative is presented by the Physical Sciences Consultorium. PSC is dedicated to explaining science with clarity, rigor, and real-world relevance, especially where science intersects with law and society. One of the most common questions asked after a suspicious death is simple: when did death occur? This question carries enormous legal weight because it can confirm or contradict witness statements. It can also reshape the direction of an investigation. Time of death is never directly observed. It is always inferred from physical and biological indicators left behind after death. Forensic physics plays a central role in this inference by treating time as a physical problem rather than a narrative claim. In popular media, time of death appears exact and precise. A specific hour is often announced confidently by investigators. In reality, science never provides a single timestamp. Instead, forensic science provides a range constrained by physical laws. Understanding why requires a change in perspective. The human body must be seen as a physical system. Before death, the body actively regulates its temperature. Metabolism continuously produces heat to keep the body warmer than its surroundings. The body exists in a state of dynamic thermal balance. Death disrupts this balance immediately. Internal heat production stops, and active regulation ceases. From that moment onward, the body begins to cool. Cooling becomes a passive physical process governed by thermodynamics. Forensic physics focuses on this cooling behavior. Heat loss effectively becomes a natural clock. After death, the body is no longer biologically controlled. It behaves like a warm object placed in a cooler environment. Heat flows from warmer regions to cooler ones. This heat flow follows predictable physical principles. It does not depend on intention, identity, or circumstance. Physics constrains how temperature changes with time. The rate of cooling depends strongly on the temperature difference between the body and its surroundings. Larger differences lead to faster heat loss. As the body cools, this difference decreases. Because the temperature difference decreases with time, cooling slows down. This produces a characteristic cooling curve. Such curves contain information about elapsed time. Forensic investigators often measure core body temperature. This temperature reflects internal heat loss more reliably than surface temperature. However, temperature alone is not enough. Measured temperature must be interpreted using a physical model. This is where physics enters decisively. A theoretical framework is required to relate temperature to time. One of the most widely used models is Newton's law of cooling. Despite its simplicity, it is remarkably effective for forensic estimation. The law provides an approximate relationship between cooling rate and temperature difference. Newton's law states that the rate of cooling is proportional to the temperature difference between an object and its surroundings. The law is empirical rather than exact. It does not describe microscopic heat transfer. Instead, it provides a macroscopic rule that works reasonably well in many situations. For forensic purposes, approximation is sufficient. Exactness is neither possible nor required. Using this model, investigators compare measured temperature with expected cooling behavior. From this comparison, they estimate the time since death. This estimate is called the post-mortem interval. The post-mortem interval is never a single value. It is always expressed as a range. This reflects both measurement uncertainty and environmental variability. At this point, an important clarification is necessary. The human body is not a uniform object. It does not cool evenly in all regions. Skin cools faster than internal organs. Contact with surfaces alters heat flow. Air movement, humidity, and clothing also influence cooling. Environmental conditions strongly affect cooling behavior. Physics cannot ignore these variables. Forensic physics therefore treats the body as a system interacting continuously with its surroundings. Ambient temperature is a critical factor. A body cools faster in cold environments and more slowly in warm ones. Outdoor conditions introduce additional complexity. Body posture and surface contact matter. A body in contact with the ground cools differently than one suspended or supported. Surface area directly affects heat exchange. Body size and composition also play a role. Fat tissue acts as insulation, slowing heat loss. Larger bodies generally retain heat longer than smaller bodies. All these factors modify the cooling curve. They must be considered together rather than in isolation. This is why time of death estimates vary. Two bodies may cool differently even under similar conditions. Forensic physics does not hide this variability. Instead, it incorporates it into uncertainty estimates. The goal is not to determine an exact moment of death. The goal is to constrain plausible time windows. This approach aligns naturally with legal reasoning. Courts prefer honest ranges over false precision. In courtroom testimony, experts explain assumptions and limitations clearly. Transparency strengthens credibility. At this stage, physics has completed its primary task. It has constrained time using thermal behavior. In the remainder of this episode, we will examine the limits of cooling models and how courts interpret uncertainty responsibly. While Newton's law of cooling is extremely useful, it is not a perfect description of reality. Forensic physics must always recognize the limits of its models. Crime scenes rarely match ideal conditions assumed in theory. The law assumes a relatively simple environment. In practice, bodies interact continuously with their surroundings. Heat transfer becomes complex and situation-dependent. Heat can leave the body through conduction, convection, and radiation. Each mechanism contributes differently depending on conditions. Their combined effect shapes the cooling curve. Contact with the ground increases conductive heat loss. Air movement enhances convective cooling. Radiation becomes important when temperature differences are large. Clothing alters all three heat transfer mechanisms. It can trap air and slow cooling. Wet clothing can accelerate heat loss instead. Because of these factors, no two cooling curves are exactly the same. There is no universal curve for all cases. This variability is unavoidable. Forensic physics therefore never claims precision beyond what data allows. Time of death estimates always include uncertainty. This uncertainty reflects honest science. A common misconception is that physics can determine the exact time of death. Popular media often reinforces this belief. In reality, exact determination is impossible. Physics does not provide timestamps. It provides physical constraints. It narrows what is plausible and excludes what is not. Another misconception is that early cooling is linear. Cooling is not linear over time. It slows progressively as temperature differences decrease. Ignoring this behavior introduces systematic errors. Oversimplified calculations can be misleading. Forensic physics avoids such shortcuts. Errors may also arise from improper temperature measurement. Core temperature must be measured carefully. Surface temperature is unreliable for timing. Environmental temperature must be recorded accurately. Incorrect assumptions about surroundings distort results. Small errors can shift the estimated time window. Forensic experts therefore document all assumptions explicitly. They state environmental conditions clearly. Transparency is essential. In court, these assumptions are examined closely. Cross-examination often focuses on limitations. Experts are expected to justify uncertainty ranges. Courts do not expect exact answers from science. They expect defensible reasoning. A well-explained range is more credible than false certainty. Judges and juries are informed that time of death is an estimate. It is not a clock reading. This distinction prevents overinterpretation. Thermal analysis is rarely used in isolation. It is combined with biological and chemical indicators. Multiple lines of evidence strengthen conclusions. However, physics sets boundaries that cannot be crossed. Any proposed timeline must obey thermodynamic laws. Physics acts as a filter against impossible claims. If a narrative contradicts heat transfer principles, it must be rejected. No testimony can override physical law. This is the protective role of physics. At the same time, forensic physics remains neutral. It does not accuse or defend. It informs legal reasoning without bias. This neutrality strengthens justice. Physics serves truth rather than outcomes. Its role is constraint, not judgment. This episode has shown how heat loss becomes a clock. It has also shown why that clock is imperfect. Scientific humility is essential. Recognizing limits is as important as applying models. This distinguishes real forensic physics from fiction. Reasoning matters more than spectacle. This series is presented by the Physical Sciences Consultorium. PSC is committed to explaining science with clarity and responsibility. The goal is understanding, not sensationalism. If you find this series valuable, please like this video and share it with students and educators. Subscribing to the channel supports future episodes and sustained educational outreach. In the next episode, we move from time to motion on a larger scale. We examine accident and crash reconstruction using physics. Energy, momentum, and kinematics will again guide analysis.